Let me thank Rakesh first. A very fantastic arrangement, Rakesh, so far. So, what I'll do is I'll plan to give a very brief introduction to some of the known phases, known ordering in magnetism, especially keeping in mind the student audience, which has reduced a lot by now. But I'll continue the plan that I had, and then try to touch upon a new phase that people have started looking at more recently, and how symmetries plays a very key role in these kinds of new kind of magnetic ordering. That's one part of my talk. The other part will also touch upon some of the topological features of a real material which has been simulated by my students and subsequently synthesized by our experimental collaborator. So that brings me to first acknowledge the people who are involved in this project, and these are mostly at the research level problems that is being that I'll show towards the second half of my talk. So Kenta Kuroda and Kimura has been the experimental collaborator from Hiroshima University, who helped us to do some of the angle resolved photo emission spectroscopy spectra to understand the topological feature of this of one of the material that I'll show. That's just a test case. Shayantika, who was in ETH Zurich, who helped us to do some of the multipole simulation, which are very important to understand this kind of unconventional magnetism. And Shayantika is now actually one of our colleague in the Department of Physics, IIT Bombay. He joined us recently. KG Suresh is again an experimentalist, mostly a transport and single crystal growth expertise in our department. And the actual main people who spent a lot of time to do the simulation and some of the experiments. Jadupati Nag, who used to be one of my student and now a postdoc in Penn State, and Bishal Das, who did all the simulation. So let me start with introducing some of the conventional magnetism that we know. And if I talk about magnetic materials, there are broadly two classes: collinear order, non-collinear order. Under collinear, I can have ferromagnetism, I can have antiferromagnetism, and each of them have their own features. Ferromagnets, where all the spins at different sublattices are up, for example, and antiferromagnets are like, if I can think of the nearby spin sublattices to be oppositely aligned, and they have their own band dispersion or the band structure. We think in that way. The other unconventional magnetic orders are non-collinear order, and under non-collinear I can have a coplanar, which is such as helical order, or I can have non-coplanar. These are all magnetic structures which are found in real materials, and skyrmions are one of the well-known and well-studied magnetic structure people have studied. We can also have ferrimagnets. Ferrimagnets are basically they may have different or inequivalent sublattices with different moments on each of them, such that there is a net magnetization that I can get if I sum them all up. Now it can have a partially compensated moments, or it can have a fully compensated moments, depending on how these spins are arranged and what are their individual moments on those sublattices. And from textbooks analysis, we do understand the ferromagnets, the antiferromagnets, because each of them have their own susceptibility, rather temperature dependence of susceptibility. Antiferromagnets are very well known for their Néel temperature and so on. Some of these do not have very well documented, theories, but there are experimental signatures which help to identify what these properties are. Ferrimagnets again are another class of collinear order, which can be any of these two types. So these are all conventional magnetism. However, there are some features which people have recently found. And if I can quickly draw a schematic. So all of us know Ising model, where we have spins arranged like this, right? Such that my neighboring spins, this is a model for the antiferromagnetic case, where I have, if I sit at any particular sublattice, spin sublattice, I have opposite spins aligned in my nearest neighbors, if I see a square lattice kind of thing. And, people have solved Ising model for this. This is a AFM case, but then there are also FM counterpart of this. And this is something which is exactly solvable, and there are magnetization, there are various properties that one can calculate by just writing the Hamiltonian as J SI dot Sj. That's the simplest Hamiltonian. I can have a field also on the top of this. So this is something which comes under the purview of these kinds of ordering, ferromagnets, antiferromagnets. But if I, in a very simplistic picture, if I can introduce something which is non-magnetic in nature, in the sense that if I can have a sublattice which also is there in this particular lattice structure, such as this, that I have this is also a similar like Ising model, but what I have done is, let me change this structure a little bit. Let me have another one. All right. So in a very simplistic picture, what this is, the way it is modified as compared to Ising model is that, of course, I have spin-spin interactions, which are like down all has up in its neighbors. But then I have included also some other elements which are non-magnetic in nature, which means these interactions are different than, they will also have interactions with these in the sense how they are arranged, right? However, there is one important difference that you can see. If I sit at a particular lattice, say I'm sitting at this place, my environment is, if I look at the non-magnetic environment, it has OO along horizontal and square along this. But if I go to the sublattice where I have a spin down, this one does not have the same environment at this, right? Because here it is square along horizontal and circle along the vertical. However, you can actually go from here to here by a specific kind of transformation. What you need to do, if I am sitting at this place, I'll first do a spin inversion. So this spin will flip. I will have to then rotate this so that this comes here, this comes here, this comes here. And if I then translate it here, this will replicate exactly the same environment as this. So by the virtue of this non-magnetic element, these two sublattices are no longer equivalent. Unlike in Ising model, where I am sitting at a particular spin, say up, all my neighboring sides are down. They are exactly equivalent. Or if I am sitting at a spin down, my neighboring sides are all up. But this is not the case. So in the conventional antiferromagnetism, the transformation going from spin up to spin down or spin down to spin up is a simple translation. or it can be an inversion. But in this case, it's more of a rotational transformation, right? Until and unless you sit at a particular site and rotate, you cannot mimic the other sublattice. Now, people have been exploring this kind of a magnetic order where there are non-magnetic sites in addition to magnetic sites. And what is found is that there are some very different kind of features that you starts to see, and the consequences arises in terms of the reciprocal space representation of these. So this is a real space picture of this lattice of this sublattice, but I can also solve this problem in the reciprocal space where I will have a band, right? We from textbooks knowledge, if I have a periodic lattice, I will have a band dispersion. And the difference, so had this been a conventionalizing model, and if they are perfectly antiferromagnetic, if I look at the bands for the spin up and the spin down, they will be exactly mirror symmetric to each other, right? However, if you look at the bands for this kind of a lattice, they will not be exactly mirror symmetric. In fact, there are certain directions in your bands where you will see that there are splitting, which is not very straightforward to understand. And hence the symmetry becomes very important in these kinds of new kinds of magnetic order.
Just a quick clarification.
Yes.
You said that for a ferromagnet, it's simple translation, and for antiferromagnet, it's spin flip followed by a rotation.
No, in conventional antiferromagnetic, if you don't have these sublattices, then also it's a translation, right? It's just you do the inversion, spin inversion, translate it, you'll get back to the other sublattice. But here you won't, because this whole part does not mimic this part unless and until you rotate by 90 degrees.
You don't want to talk about ferromagnet.
Well, yeah, I mean, antiferromagnetic is more interesting because you have mirror symmetric band structure, but you won't see mirror symmetric if you have this kind of a modification in your simple Ising chains. Okay. So interestingly, this is just a very simple picture which I am showing here. Interestingly, there are real materials which also shows this kind of a situation where you have two magnetic sublattices. They are antiferromagnetically coupled, but because of these non-magnetic elements, their environment are not same, and hence it becomes different, especially because of this very symmetry I'm talking about. All right, so that brings me to just discuss very quickly some of the group theoretical analysis of magnetic crystals. Okay, so this is the spins in magnetic crystals, and what I am really showing it here is exactly something which I have already described, that I have various sublattices. These squares basically show there is no correlation between this square and this square. These are all sublattices where you have a magnetic element here which has a spin up. There is another magnetic element. All these are spins up. So this arrow is showing the spins. This square is showing the crystal sites with the magnetic atom. And yeah, so there are certain symmetries they follow, and there are magnetic space groups and the spin groups which can connect from one to the other. For a simple ferromagnetic, there is this is absolutely clear. But if I go to a slightly different environment, oops. Let me come here. Yeah. So apparently there are a couple of symmetries which one need to be very careful. One is the space inversion, the other is the time reversal symmetry. So if I apply the space inversion or parity, my real space and the k space gets affected, but the spin is unaffected. But under time reversal symmetry, my k and s both will reverse, but the real space will remain unaffected here. This is a transformation which is for a ferromagnetic case. For example, C infinity is a very infinitesimal transformation which does not change my sublattice, and this is a spatial transformation which C2 is basically a transformation which acts on the sublattice and it rotates this by 180 degrees. So this will, you can see that they flip. But then if I apply the time reversal symmetry, the spins comes back, and then you get back the same kind of symmetry, the same thing as you have started with. So C2 bar is a very special symmetry which connects these two inversion. Similarly, for antiferromagnetic case, where I have a down spin in the center and the up in the background, you will see that C2 bar again takes you back to the same configuration you started with. Now, if I am moving to the K space, because the K space is more interesting and it shows some very different features. If I have a ferromagnetic, my band structure, which is E as a function of K, it will split. That's the first thing. So the two lines basically are showing the one is for the spin up, the other is for spin down. There are certain symmetries that they will follow. If I am moving from 0 to K or 0 to minus K, the band dispersion will follow this relation. Similarly, for the down spin, I will have K or minus K. It should show the same energy. If I have an antiferromagnet, then as I said, if it is a conventional antiferromagnet, the spin up and spin down, I cannot distinguish between them, which means I sit at any point K, my spin up and spin down has to be same. The K and minus K relation also holds true for both spin up and spin down. Okay, this is conventional. However, if I have alternating spins, which is a similar situation like this, which means my spin sublattices does not have same environment around it, in that case, you will get a splitting in the bands, unlike a conventional case. This is a conventional case, but in this particular situation, because of the certain symmetry, satisfied by this, and especially the rotational symmetry, you will see that at some K point, these up and the down bands are split. There are of course few points where they are degenerate, just like the conventional antiferromagnetism, but there will be some path or the K where they will be non-degenerate. And this is something which you can show by just doing simple calculation, but people have found this in real material also. Okay, so this is just another cartoon picture to show the same thing. If I have say ferromagnetic case, I cannot distinguish between this and this. These are all spin ups, right, all over the place. All the sublattices are spin up. However, if I have an conventional antiferromagnet, where one of the sublattice is spin up, the other is spin down, I can simply translate from here to go from spin up to down. Or I can, I can do an inversion to get back from one sublattice to other. In this case, you cannot. If you simply translate from here to here, you will not get this shape. And that's what I'm talking about here also. In order to go from spin up to spin down, you have to do a 90-degree rotation to match this shape. If you rotate it by 90 degrees, then only you will be able to match. And that is going to reflect in your reciprocal space band structure. Now you can always ask, okay, so what? There are splitting in the band structure. It turns out that such splitting actually has a consequence on your material properties, such as, there are Hall properties. There are also other transport properties which will be different as compared to the simple case. Okay, as I said that this talk also has a topological, physics aspect, but I'll not go into the detail because I think Saurabh has already covered this in the morning. So this is basically some, cartoon diagram to show the genus as you do the, the smooth deformation from one to the other. So I'll quickly go. So this one is again a very quick diagram how to understand topology in the condensed matter systems. So you may have a normal insulator, and depending on some external parameters such as pressure or strength of the spin orbit coupling, you can actually close this gap, and this is still a trivial Dirac semi-metal because these are four-fold degenerate. You can have a band inversion, which is a signature of your non of your topological phases, and you can have a topological insulator where the gaps is open. You can also arrive at a topological semi-metal where the bands are actually overlapping into each other. And depending on what symmetry you break, suppose you break the time reversal symmetry, you can actually arrive at a Weil semi-metal phase, which are twofold and they always come in pair. So these are some of the fundamental features that you see, the consequence of topology in condensed matter. There has been a plethora of different materials that people have come up to show these properties. For example, tantalum arsenide, which shows a Weil semi-metal phase, which means going from a four-fold degenerate Dirac semi-metal to a Weil semi-metal, where the inversion symmetry is broken. There are also cases where people show that if I break time reversal symmetry, such as in Mn3Sn, you can arrive at a Weil semi-metal phase. The question is, there are cases where both of these symmetries are broken, and then what kind of physics that you get out of it. Okay, so this is just the motivation or the introduction to this kind of a magnetic ordered phase. What we have found, and this is the actual backbone behind the work done by many people, as I showed in the first slide, we found that this kind of a feature is actually realizable in a real material system, gadolinium aluminum silicide. And because there are certain symmetries broken in this system, such as the inversion symmetry and the time reversal symmetries, there are also topological Weil semi-metal phase that come up in the band structure of this compound. You can switch off this light. Yeah. Okay. So, so what we had initially done is Bishal had simulated this material because he had been working and trying to understand the physics of this kind of unconventional magnetism. And he found that this particular system, if you analyze its crystal structure, it actually has a similar feature in this. There is a non-magnetic element, which is aluminum and silicon. You can imagine this as square as, say, aluminum, circle as silicon, and gadolinium has its moment, which are arranged antiferromagnetically. And he simulated this, and initially we were quite puzzled because your band structure shows a lattice, a spin splitting. And we were not so much well versed at that time that, oh, this kind of a physics can give you a spin splitting. But then later on, we realized that if you solve a problem like this, you can actually get spin splitting in certain directions. And so bottom line is this calculations was done first in this project, and then it was given to the experimentalists to verify some of these findings. Okay, so just to motivate why this GDAL-SI, what is so important in that, there are certain background, and it turns out that there are several systems, there are several material systems in this belonging to this class, which people have studied, over a period of time. You can see that these are a bunch of papers coming out on similar class, and they showed various kinds of magnetism, starting from polyparamagnet, ferromagnet, antiferromagnet, and there are some helical phases also. And they have different transition temperatures, different effective moments. However, none of these studies have really looked at that aspect of these systems, although most of them maintain that symmetry. Okay, coming back to the crystal growth, because that is one of the very important thing. All of these materials actually has been synthesized by several groups. This is a paper where the crystal growth data of all these systems are being reported. An important thing here is that in some of these systems, people found that this aluminum and silicon actually come in a disordered fashion. What it means is that you don't have a control on whether this site is a square or a circle. So each of these non-magnetic sites are absolutely disordered in nature. This changes the symmetry of the crystal, because if I cannot distinguish, or if these non-magnetic sites are completely randomly occupied, it makes it a centrosymmetric system. However, if they are identifiable like this, that I know that aluminum has to sit here or silicon has to sit here, they belong to a non-centrosymmetric system. So one need to be very careful. If I suppose synthesize one of these compounds, I need to make sure whether these non-magnetic elements are coming in the disordered fashion or they are sitting exactly at the site what we are looking at. So these are some of the representative cases in this class. I will probably not go into much of a detail, but I'll quickly tell that praseodymium. So lanthanum, cerium, praseodymium, neodymium, samarium, europium. All of these are F electron systems, so they are strongly correlated. Okay, so yeah, so what people have studied in all of these is mainly the topological physics of these systems, which means what are the kind of topological bands feature that you get out of this. And as I said, depending on whether aluminum and silicon are mixed in a random fashion or they are occupying the sites accurately, their symmetries are different. But in most of the cases, the time reversal symmetry is broken, and hence the Weil semimetal phase is one of the things people have studied in all of these. So you can see that this is a kind of a non-magnetic test case, lanthanum, aluminum, germanium. But this is because there is an inversion symmetry breaking, there is a Weil kind of a phase. You can see here, and this is basically a type 2 kind of Weil. There can be two types of Weil phase. One is if the crossings are absolutely linear or if they are bent. So in this case, they have found type 2 kind of a Weil semimetal phase. They have also studied another example, praseodymium, aluminum, germanium, and they found it to be a ferromagnetic phase. And these are.
If we go back to the previous slide, there was a word there I didn't quite understand. You said Lorentz violet. What can you expand on that?
So this is basically related to the symmetry of this crystal. I will show the crystal structure of this. So depending on this crystal structure, and as I said, whether aluminum and silicon are exactly sitting at its own position or they are randomly, occupying substitutional disorder, this Lorentz violation is always there. You can write down the equation to see this. I'll show you the crystal structure. So the phenomena is there are certain symmetries in this system. One of them is the time reversal symmetry is broken because they are either ferromagnetic or antiferromagnetic. And also, if you look at the crystal structure, the inversion symmetry is broken. Now, if any of these symmetries are broken, you are expected to get a topological Weil kind of a physics. If you plot the band structure, the band dispersion, you will see that you have a pair of Weil crossings which are twofold in nature. So Weil physics is one of the things which people have captured in most of these compounds. But the magnetism side is something which people have always missed. So it seems like depending on the symmetry of these class of systems, there are two coexisting phases. One is the Weil physics, the other is the altermagnetic physics, which people should check, and that's one of the target of our work. Okay, so this is again another example, neodymium aluminum silicide, and people have looked at various kinds of magnetic transition here. One is commensurate magnetic order, the other is incommensurate. But bottom line is that in all of these studies, people have mainly looked at the topological physics of this. All right, now let me come to the GD-ALSI system, which we have studied, and why they are important and what is the different aspect that we have looked at for this system. So this has been crystallized by our experimental group. Then, among this family, gadolinium has the highest moment. There are unconventional magnetic ordering, which I will show in a few minutes, and there are topological Weil physics that we have, and we have done the ab initio simulation to understand them. So just to show some of the experimental data which was done by Professor K.G. Suresh, this is a single crystal X-ray diffraction data, as you can see here. This is the crystal structure, and it remains in a body-centered cubic phase. Let's not worry about the spins right now. This is just a representative, figure. But some of the details of this crystal growth for colleagues who are doing experimental, materials physics. This is synthesized by using self-flux method, starting with elemental ratio 1:15:1, and it is done in an aluminum crucible with sealed quartz. In order to confirm that we indeed have a 1:1:1 ratio of this, because there may be off stoichiometry of gadolinium, aluminum, and silicon. They have done EDX measurements in Loy diffraction pattern, which basically shows that their ratios, the individual ratio of gadolinium, aluminum, and silicon are almost 1:1:1. Now, as I said, there is a very important catch here, whether aluminum and the silicon, these two non-magnetic elements, whether they are forming in a disordered fashion, or they are sitting exactly at the position I have drawn here. There is a measurement, there is a probe, it's called second harmonic generation measurements, which basically are sensitive to systems which are non-centrosymmetric, which means where the inversion symmetry is broken. In a very layman sense, it's basically it's a basically non linear optical measurements, where if you shine two photons with each of frequency omega, it actually gives rise to a single photon with frequency 2 omega. And if it is having a, if it is sensitive to the inversion symmetry breaking, it shows certain intensity in this, which confirms that the inversion symmetry is broken, and hence these non-magnetic elements, which means aluminum and silicon, are sitting at their own position rather than being mixed into one another. So there are more experimental details which my friends, colleagues know much better. There are some measurements, magnetic measurements, which was done by them, and you can see that if I look at MT data, there is a small kink here, and the same kink is also observed in the resistivity versus temperature data, which basically give an indication that there is a phase transition below 32 Kelvin, and above it, usually have a paramagnetic phase. So a noticeable deviation occur at 32 Kelvin. And there is a similar kind of a transition here. The question is, what kind of transition, what kind of magnetic ordering persists here? So in order to check what is the magnetic ordering that holds below 32 Kelvin, we could not do neutron diffraction, which is one of the probe to find out the actual magnetic ordering. But we did the simulation of various types of magnetic ordering, and you can see these are different magnetic arrangements which were designed and simulated. And the idea is, out of all of these magnetic configuration, which one is the lowest in energy, because they are the most likely to show up in the actual material. So you can see that AFM1, this is the relative energy difference, and AFM1 is the lowest. All the others have higher energy, milli electron volt. AFM1, which is this, which is nothing but a layer-wise antiferromagnetic arrangement. They are the lowest in energy with a magnetic moment this. So considering that this is most likely to happen in the real material, we took this and proceeded to do the band structure calculations. Now, let us focus on this particular plot. which is the band structure without including spin orbit coupling, which means I can plot the spin up band structure and the spin down band structure, which is shown by the blue and the red line. You can notice that had this been a conventional antiferromagnet, which means that I don't have this sublattice inequivalency like this, I would not expect the blue and the red lines to be distinct from each other. But you can see that in certain high symmetry direction, certain K path, the blue and the red are indeed different from each other. However, there are also other paths where they are actually degenerate, they spin up and down. Now, this can be seen from here. This is the corresponding Brillouin zone for this particular compound. And you can see that the direction in which they are non-degenerate are basically starting from gamma, sigma, n, sigma 1, z, which is this plane. And also there is another plane, which is this particular plane. These are the two planes where they are non-degenerate. There is a plane where they are degenerate, and that plane is basically a plane which is coming diagonally opposite to this. So that there are two planes like this. In this plane it is non-degenerate, in this plane also it is non-degenerate, but a plane coming out of, diagonally coming out of this has certain degeneracy in this. This is again arising out of the symmetry from the real space, because this symmetry actually dictates your Brillouin zone, and that inequivalency is arising in the form of this band structure. This is the band structure where we have included the effect of spin orbit coupling. And what turns out that this splitting is larger as compared to the splitting, because you can also expect certain splitting which comes because of the spin orbit coupling. And they are much smaller than this particular splitting. And as I said, the consequence of this splitting comes in the form of the properties of the material.
So in both the plots, there are some nodes which are touching each other. Peak, inverted peak and the peak, but those signify something?
Yes, yes. So that's where the topological physics comes in. So far I'm mainly concentrating on the altermagnetic part, where there are splittings in certain directions, although I should not expect for a perfect antiferromagnet. But because this is not a perfect antiferromagnetic, there is still splitting, which is not expected. But then, yes, I am coming to the crossing part. Yes, that's the other physics that these compounds have. Hmm?
So when you did the simulation to find the minimum energy, what Hamiltonian did you use?
So these are all electron Hamiltonian, where I have taken all the interactions between gadolinium, silicon, aluminum, and so on, and then calculate using density functional theory. So these are all electron density functional theory calculations.
Impurity, some of
In this case, there is no impurity. All of these sites are occupying their own position. So there are definite positions for each of these atomic sites. So that asymmetry, that asymmetry is also reflected in your Fermi surface. You can see that this is the band, this is the Fermi surface for a spin down, this is the Fermi surface for a spin up, and they are actually connected by a 90-degree rotation. You can see that if you rotate it by 90 degree, you get this. So there are certain reflection of the real space properties in the K space. This is again the similar thing, how these sublattice dependence are playing a role here, and why there are splittings in certain direction for this unconventional kind of magnetic ordering. All right. There are also ways to better understand these, these findings. And, just like here, where this is just a simple two-dimensional picture of it, because it is easy to visualize. In this 3D picture also, you have a similar kind of transformation. So each of these pyramid basically is enclosing the spins. So this is a pyramid which is like this. This has a spin up, and then there is a pyramid here which has a spin down. And the reason I have shaded them differently, because they actually are different in terms of their environment. and you can only go from here to here by making a similar kind of transformation. This is up, this is down, probably it's not visible, but in order to go from here to here, I have to first invert the spin and then rotate this. So basically in this case, just like that, each of these gadolinium which has a spin has a aluminum and silicon surrounding that spins, and you can go from here to here only if you make a spin inversion and then you rotate by uh, by a 90-degree here, and then you translate. So this is the transformation, C2C4Z transformation, which can map one sublattice to the other sublattice. And there are other systems also where this kind of a transformation, there is a rotation that you need to do here instead of simple translation. And this is basically originating from a similar sublattice mapping as in the two-dimensional case. So,
How do you know that these states?
which one?
The next, the one that you showed me, the two states. Yeah.
Huh?
Is it correct? These are some states, right? Of the
You mean these?
whole configuration.
This one?
Yeah.
No, this is just two different motifs of showing the same crystal structure. What I'm trying to convince you is, how can I go from this sublattice to this sublattice? Had this been a conventional Ising model where I have spin up and then spin down in my neighbor, so say for a square lattice, I just need to translate. I just need to invert one of the spin and translate to my neighbors to get that sublattice. But in this case, I will not be able to do it. Just for example, here,
It's the symmetry of the Hamiltonian.
it's the symmetry of the crystal and the magnetic. So there are two kinds of symmetry. One is the real space symmetry, the other is the magnetic symmetry. And you have to act on both of them. Just like here also, if I want to go from here to here, I have to flip the spin and then I have to do a rotation locally around this. Then only I can replicate this, right?
So, sorry.
Well, I can write down a Hamiltonian.
Maybe my question is, when you plot this to me, it's like a state, specific state. So, one
So it's a configuration. It's a magnetic ordering. It's a magnetic configuration of the system I'm trying to calculate.
say that you will find symmetry which keeps this invariant somehow. That's the question.
No, I'm trying to say that there are certain symmetries which are different in this case as compared to conventional antiferromagnet.
How will they show up in Hamiltonian, in the spectrum?
Oh, so this is the generic Hamiltonian for a Ising model, where I don't have these, right? These are only spins. Say I have a square lattice where each side is surrounded by opposite kind of spins. This will do it because I don't have to care anything about others. But if I want to simulate this, my Hamiltonian will definitely have this, which is the interaction between each of these spins. But then I cannot forget these because there are also environmental effect that it is showing, and that will act on my Hamiltonian.
So these operations will leave the Hamiltonian invariant.
Correct. Yes. So for example, here also, if I invert the spin and then I rotate this, so if I just focus on this particular spin, right? So this is my environment, but I can go from here to here only if I rotate it by 90-degree so that these are replicated.
One more question.
Ah.
Time reversal symmetry gives Kram's degeneracy. What happens to that here?
So time reversal symmetry will be broken here also.
So
If
can you show it up? Suppose can I check that there was Kram's degeneracy and that this configuration breaks it somehow.
no, only if I connect it with that transformation, then only I can go from here to here, and the time reversal symmetry is broken in the system by the virtue of their spontaneous magnetization. But there is an inversion symmetry also. So unlike the Ising model where none of these were there, it was only possible if I do a translation.
But
Right?
after your band structure would also say they're broken.
Correct. Yes, yes. So that's why I showed that.
Up K and a minus down K.
Correct, correct. You
So it's not spontaneously broken. Time reversal symmetry. It was spontaneous.
Then is it explicitly broken because of this?
It is broken, explicitly broken for this.
Magnetism will flip the magnetic fields.
Correct.
Right? So then I can flip the magnetic field and translate.
Huh.
So if I do these two operations together, maybe there is such a symmetry still.
Correct. But in this case, simple translation will not do this.
Okay. Do time reversal, translate, rotate.
Correct. So you have to have an additional operation.
I understand. But will that show up in the, does it show up in the eventually?
Correct. Yes, yes.
Yes.
It will. Yes, of course.
But,
That
is there any canting in the real material?
we cannot do neutron diffraction here, which is one of the probe because of the gadolinium. It will absorb the entire neutron. But then there are systems like MNTE, which is also a candidate to show this kind of a material, this kind of a altermagnet, and people have found that if it is if there are canting in this, then altermagnetism will be gone. It has to have a collinear antiferromagnetic ordering. Okay. Okay.
You can't have DMI and stuff.
Well, there will be DMI interaction, but what turns out that these splitting, which is non-relativistic in nature, is much more stronger than your spin orbit coupling. So they win over the any consequence like anomalous Hall or anything like that. So one need to find a system where this splitting is stronger. Okay, this is just a quick demonstration of how sensitive are my band structure in terms of showing spin up and spin down. As I change these environment, or as I make this up and this down. Okay, so what is interesting is that in these kinds of systems, the multipolar contribution in your charge density starts to show up, and these are very high order multipole, like magnetic octopole or charge quadrupole. So this is what we have calculated just by considering its environment around it. And if I start from here, which is the original structure, which is this, and I change the magnetic domain, what it means is that I make spin down, spin up, and I change spin up to spin down, which means I'm changing my spin environment. You can see that these values actually changes. So if I go from here to here, so the squares are the charge quadrupole, but the two sphere and the diamond are basically magnetic octopole. So spin is going to act on the magnetic octopole, and you can see that they become reverse. This is a structural change, which means what if I exchange the position of aluminum and silicon? That is also going to change my environment of what spin I'm talking about. So going from here to here is a structural change, and that also reverse my octopole and the quadrupole. And how it affects the band structure, you can see that if I go from here to here, which is like the corresponding band structure from here to here, the spin up becomes down here and spin down becomes up. So by changing this environment or by changing the spin orientation, I can actually manipulate the spin energy position. And finally, if I do both magnetic as well as structural change, I get back to the original one. Okay.
So you in the left-hand side plot.
This one.
Yeah. So you have in each quadrant you have two sort of data points.
Three.
Okay.
So one of them is quadrupole.
Okay.
The other two are the tensor elements of the magnetic octopole. So there are two of them.
Going from when you only change the magnetic
Domain.
Yeah. Then the quadrupole is not changing.
Correct, because I'm only changing the spin. Magnetic domain means it's only act on this. But if I change the environment, then your charge quadrupole is going to get affected. So this is one of. Correct. No, that is exactly why I'm showing this, in order to better understand how sensitive is your splitting. This band, why this band structure is splitting. What is the origin behind that? So the purpose here is to show that this environment are very important. How how are these non-magnetic elements are, the square and the circle, right? If I change these environment, it should also affect your band structure. Or if I change spin up to spin down, which is like magnetic domain change, you will see those effects in your band structure just like this. No, there is no increase or decrease. They are just flipping. So no. So consider this as one plot. A as one plot. What I'm plotting is the value of these multipoles for this particular configuration. Say I started with this. When I so it is not an increasing or decreasing. I'm just showing that if I do a structural change, which means wherever aluminum was, I replace it by silicon, or in this case, wherever square was, I replace it by circle, and circle is replaced by square, which means I have somehow changed the environment at a particular sublattice. And because it is a surrounding environment change, it actually flips the sign. Correct. Yeah. Because there is a transformation which. Correct. But if I go for a magnetic domain change, which is like spin thing, it acts on the magnetic octopole. So what it says is that there is a sensitivity of these environment, which is what we are talking about. All we are talking about is how these environments are changing your band structure, right? So this is just to show that they indeed are very sensitive to the position as well as the spin inversion. Okay. How much time I have, sir?
You have 25 minutes.
All right. Okay. So, one of the consequences of these spin splitting is reflected in your anomalous Hall effect, which are again mediated by Berry curvature, which of course, is very, well known in these kinds of systems. So this is just to show the spin projected band structure, where this is a continuous change in the spin from -1 to +1 or up to down. And you can see that in this regime it is almost same, no change in the up and down, but then there are directions where there are changes. And as Rakesh pointed out, there are several crossings over here, and these crossings, if they are non-trivial in nature, it will show up in the Berry curvature. And you can see that there's a huge kink in the Berry curvature, which will eventually sum out into and show in the anomalous Hall effects. All right, coming back to the other physics which people have looked at extensively in this class of system, which is the topological physics of this. And coming back, these are mainly coming from the band structure topology in these locations where there are certain crossings. And correct. So what we have done is, because this is a gigantic reciprocal space, we have chosen the entire Brillouin zone and tried to find out in the entire Brillouin zone what are the energy positions where they are having a band crossing, and what is the chirality, because if they are indeed non-trivially while, they have to have a chirality +1 and -1. And this table basically shows that these are the Cartesian, the reciprocal space coordinates, and these are the energy position with respect to your Fermi level where you have these band crossings. And these points, blue and the red, basically shows one of those crossing is with chirality +1, the other is with chirality -1. This is just a different motif of the same. And you can see that some of these while points are of type 2, while some others are type 1, depending on what is their nature of this crossing. And this is just to show that I'm just showing a few representative cases of 32 while crossings. Some of them are indeed type 1 in nature, and that's how we distinguish some of the crossings to be type 1 or type 2. You can see this is mostly like a type 1, but here this is also a crossing, but they are bent, but they are also twofold degenerate, and they have a corresponding another K point where their chirality is -1. This is again type 1 and type 2. So this is just a representation, and you can see that their positions are quite close to Fermi level, which is important because the closer these crossings to the Fermi level are, the more stronger effect it shows up in the material properties. This is again, as I said, Kimura had helped us to look at some of the band topology by using angle resolved photoemission spectroscopy. And these are some of the data from them. So this one is from the ARPES data. This one is simulated by us. You can see there are several similarities, such as this hotspot, and there are a hotspot here, and then coming down here. So you know, just to show a glimpse of certain comparison between the ARPES and the in ARPES they indeed found wild crossings like in other systems in this class.
The right hand is the imaginary part of the Green's function, I mean, the spectral function.
This one?
This is spectral function.
Correct. This is calculated, and this is measured.
That's the experiment.
Correct. Exactly. This is some Fermi arcs at 3 different energy cuts. So basically, if I look at band structure, I can have Fermi level, and then I can cut at different energy. So this is EF -200, EF -500. And again, the right-hand side plots are simulated by Vishal, and this is done by Kimura group in Japan. And you can see that, of course, there are certain similarities in each of them. We cannot exactly map one over the other because there are some differences in the material that we simulated versus the actual real material. But then you can see that there are several similarities that I can see in the two. So that brings me to the end. So before conclusion, there are certain applications point of view for these class of materials which I have not mentioned yet. You know, spintronics is one of the area where people have been studying these quite extensively in order to better and better understand. Because if I look at the history of spintronics based materials, conventionally ferromagnetic materials have been the primary choice for any spintronic based devices because of the inherent exchange splitting and spontaneous polarization. But the problem with FM ferromagnetic material is that they are quite sensitive to the external stray fields when you actually used in the devices. So people come up with collinear AFM, which do solve some problems, but then it gets stuck because there is no distinct spin polarization in the conventional collinear antiferromagnet. This problem people try to solve it by finding materials where there are non-collinear AFM, where there is a spin splitting in your band structure. So these are more recent findings of some of these exotic magnetic materials, and there are several groups who are working on these, and this field is still evolving slowly because there is no specific probe to actually understand these except you do ARPES, where you can see the exact spin splitting. And even in order to do that, you have to make sure that your spin ordering is a collinear antiferromagnetic, which means you have to do experiments like neutron diffraction and all, because if it is this, then only the physics is clear. If it is canted, then the splitting is inherent. There will be. So some of these high level experiments people are still trying to come up with and be very careful. The bottom line is this particular compound that we found, it co-hosts altermagnetism and topological wild physics. This is the first non-centrosymmetric system, which I forgot to mention. So far, whatever system people have studied in this area, in this line, are mostly centrosymmetric. And the present study facilitates a new direction to explore the emerging topological features. At the end, I really emphasize that magnetism is a key to drive exotic properties and phenomena. Thank you.
Nice talk. So, some questions?
So, is there a chance that these materials, we can say high temperature superconductivity materials? Normally, ferromagnetism and superconductivity.
There is a competition. There is a competition.
Uh,
Yes, there is a phase diagram which I saw in one of the recent Smechkel's paper, where they did a modeling basically to see that is there any regime of the strength. Remember, in order to simulate this, one need to have two more terms here. One is the strength between this and the non-magnetic element, and one is the strength between these.
Yeah.
So there are two more terms here, and by tuning those strength, they showed that there can be a regime where your resistivity may come down to a very small value. Yeah, so it's a very intricate interplay between these interaction strength. There is a chance.
But,
Yes.
but I mean, just the resistivity coming down may not be a acid test. You need to have
The-
Meissner effect
Correct.
and all of that.
Correct.
So
Yeah,
that-
yeah. So as I said, people are still trying to understand this by doing Monte Carlo and advanced.
I have a quick question. What is the strength of the spin orbit coupling vis-a-vis your J, so to say, the parent J
Correct.
ratio?
We have not calculated J as such here, but what we have seen is the splitting, which is non-relativistic spin splitting, where I have not included any spin orbit coupling. The maximum splitting is of the order of 132 milli-electron volt,
MeV, yeah.
but the spin orbit coupled mediated splitting is 70 MeV.
Okay. So it's about half.
In this system, but there are other systems where they are even much higher. About 1 electron volt is the non-relativistic spin splitting, but SOC mediated is 0.2.
Okay.
So
More.
yes.
So with the altermagnetism and these topological semi-metal fields, they always come together,
No.
or you can have
Not necessarily.
altermagnetism without
Without
the gap.
yeah. So MNTE, for example, is another system where it only comes up with the altermagnetic phase. There is no topology there. Ruthenium dioxide
So it's a phase. Altermagnetism is some.
is a magnetic phase, just like antiferromagnetic is a magnetic ordered phase. Altermagnetism is yet another magnetic phase, just like that.
So something like Landau's theory we can use to understand altermagnetism.
Yes, yes, of course. There are a number of studies where people have tried to look at that, especially from the multipolar expansion side. They actually did that.
But what would you vary it with? If you write down a functional, what is your tuning?
I will say the strengths.
J. Okay.
J, and there are three strengths actually here.
Okay.
Right? One is the spin, the other is spin non-spin, and non-magnetic, and non-magnetic non-magnetic. All of them will play a role.
See, in a skyrmion, we usually do that angle.
Angle, yeah.
do you expect that this can be explained by some kind of Landau's theory of symmetry?
There are studies, yes.
Or do you think that this is the quantum phase transition? Because quantum phase transitions don't come under the Landau paradigm.
No. There are some studies where people have done Landau theory to explain these.
So what would be the order parameter?
The order parameter, as far as I remember, they have evaluated the order parameter in terms of these exchange strengths. Depending on certain combination of them.
Strength is like a coupling constant. That is not
Correct.
order parameter is like expectation of average of
So no. What I'm saying is
Some
that they have
magnetization or something. Like that.
no. They have evaluated that in terms of these couplings.
That just means that in terms of some particular coupling constant, you see a phase transition.
Correct.
That doesn't tell you that the underlying paradigm is the Landau paradigm. Right? It doesn't tell you the mechanism for the phase transition.
It's related. That's what I was asking. Whether it's topological phases or quantum phase.
That's
So, but he's saying that these separately also exist.
From what I understood, what he just said, it seems that people have seen these by varying the coupling constants rather than making an effective model. For like you just said.
Is there a definition of altermagnetism macroscopically? Like what is it? Local magnetization area or something?
No, what people have really talked about is based on the symmetries. This is purely symmetry mediated.
So, I mean,
There is-
one thing to answer your question. I don't know, but if you write down your S operator as expectation value of S minus delta S and replace it in these terms, and then you do this energy minimization with respect to the, the constant delta S. I mean, the expectation value of S, then something may emerge.
In most of the antidermatic condition, you cannot explain well under field. Yeah.
Yes, that's true. That's true. That's true.
Because it doesn't course grade nicely.
Are there ferromagnet examples of ferromagnet you have?
No, I mean, in ferromagnetic, you have an inherent splitting already.
Oh,
So you
okay,
cannot
okay.
distinguish,
You could
between
distinguish
what is
between-
the exchange splitting
Okay.
and how is this
Okay.
kind of a splitting.
So
So
you can
antiferromagnetic is a clean example because you don't expect a splitting.
Can you have dipolar interactions here,
No.
longer range? You can't have.
It- that-
So DMI, dipolar, all are kind of
It's only the octupolar regime where they start to show up some of them.
okay.
Magnetic
Octupolar, because you said that multipolar.
Correct. That's one of the origins.
Yes.
Can I write creation annihilation operators for the spins and separately for this non-magnetic impurities and write a Hamiltonian in terms of that? Take a Fourier transform to introduce it.
Yes. Yeah.
Can
So,
you do it?
so you can write a second quantization form of these.
Do a magnon.
Give a random theory.
Correct.
Give a random theory.
Right. We have not done that, but
That's not enough. Yeah, that's not enough. That is a good starting point. That's not enough.
No, then you
I mean, what he's trying to say is that if you write it down in
No, I
terms of
understand.
a dagger and then
We have
take-
not tried.
Starting point, you want to study quantum phase transition.
Yeah, exactly.
So in your case, you haven't done neutron diffraction.
it is not doable because of gadolinium. It will absorb the entire neutron and.
How do you then find it out that these are collinear?
Oh, that is by the simulation. We simulated various magnetic ordering, collinear, non-collinear, and see which one is the lowest in energy, and then proceeded to do the band structure. So that's a question. Yes, I mean, in the real system, whether they are indeed, but there are other systems belonging to the same class where people have found this. So it's not completely overruled.
But you have worked on the real system also.
Yes. The experiments are all with respect to the real system. Correct. That's right.
All right. I guess if there are no more questions, let's thank the speaker for this wonderful talk and both the speakers. Thank you.